Student friends, now we are going to derive Stefan's fourth power law from the Planck's radiation law. In my earlier lecture, we have derived Wien's distribution law and Rayleigh's law as limiting cases of the Planck's radiation law. We have seen that the Planck's radiation law diverges towards the Wien's distribution law if you take low wavelength region, and for higher wavelength region, the Planck's radiation law diverges towards the Rayleigh's law that we have discussed in my earlier lecture. Now we are going to prove that again. The Planck's radiation law is again nothing but a limiting case of the Stefan's fourth power law. We know that Stefan's fourth power law is stated as the amount of energy radiated per unit time per unit area is directly proportional to the fourth power of the absolute temperature of the body, and that law now we are going to derive from the Planck's radiation law. We have derived a Planck's radiation law, which states that the energy density in the frequency range between nu and nu plus d nu of the black body is given as, in terms of wavelength, it is given as E lambda d lambda is equal to 8 pi hc divided by lambda raised to 5 into 1 upon e raised to hc divided by lambda kt minus 1 into this d lambda. So this is the Planck's radiation law that we have derived in earlier lectures. Also, we have seen that the same law in terms of the frequency is given as, this is nothing but E nu d nu is equal to 8 pi h into this nu cube divided by c cube into 1 upon e raised to h nu divided by kt minus 1 into this d nu. So we can call this as equation number 1. So this is the these two equations are nothing but the Planck's radiation law. This equation is in terms of wavelength, and this equation is in terms of frequency. So this equation tells that the energy density in the unit range, in the range between frequency nu and nu plus d nu. So that is how this equation is. Now we have to actually, or we have seen that if you look at the black body radiation spectrum, we have seen that this is nothing but E lambda against this lambda graph, and for particular temperature, the nature of the graph or this black body radiation spectrum is like this. So the total energy density is given as the area under the curve, and which is for all types of frequency or all types of wavelength of the radiations. So in order to calculate the total energy density consisting all wavelengths or frequencies, we have to integrate this equation, and that radiation density will be given as this E is equal to integration over all the frequencies, and using the value of E nu as 8 pi h nu cube divided by this c cube into this 1 upon e raised to h nu divided by kt minus 1 into this d nu. So this will be the total energy density for all the frequencies or all the wavelengths. We have taken here the frequency range. So this will be the total energy density. And now we have to solve this integration in order to get the total energy density And for that, we'll take this term as outside the integral, and it will be 8 pi h nu cube divided by the c cube, integration 0 to nu 1 upon e raised to h nu divided by kt minus 1 into this d nu. So we have to solve this integration in order to get the total radiation energy. Now for that, what we'll do, we'll substitute for this h nu divided by kt as yes. So we'll call it as let us consider x is equal to h nu divided by kt. So this implies nu is equal to, we have to use this as kt divided by h into this x, and therefore we have to take this as d nu differentiation. This kt and h, they are constant, and therefore we can write this as dx. So after substitution, we have to convert this variable into x, means we are you will use the value of d nu here and value of nu here. Again, if you look at the limits of the integration, then if you take nu equal to 0, means for nu is equal to 0, you will observe that x is equal to 0, and for nu is equal to again infinity, this x will equal to infinity. So the limits of integration will remain unchanged. So using all these substitutions, we can get this integration as e is equal to, we can write this as e is equal to 8 pi h divided by this c cube, and we'll use the value of nu cube as we have used nu is equal to kt divided by h. So we can write this as k cube into this t cube divided by this h cube, and into integration 0 to infinity, we can write this as x cube, or divided by, we can write this as e raised to x minus 1 into that d nu is nothing but kt divided by h into this dx. So we'll get this equation, and after solving this, you will get this as, this is nothing but this h will get cancelled, and it will be 8 pi, it will be k raised to 4 into this t raised to 4 divided by this c cube into this h cube, and this integration will be 0 to infinity x raised to 3 divided by e raised to x minus 1 into this dx. So we'll get after substitution, we'll convert the variable nu into variable x, and you will get this integration. And we have to solve this equation. I will give this equation number as 2, and I have to solve this equation. So this equation can be solved like this. For that, consider this part as this x cube divided by e raised to x minus 1. We can consider this part. We can write this as x cube into bracket e raised to x minus 1 raised to minus 1. We can write this. Or we can write this as x cube into bracket. What I will do, I will here multiply by e raised to x and divide by e raised to x into this e raised to x minus 1, this raised to minus 1. Okay. Now, or I can write this as x cube into bracket this e raised to minus x into e raised to x. I can write this as e raised to plus x, e raised to minus x, and into bracket this e raised to x minus 1 and whole raised to minus 1. So this e raised to x raised to minus 1, if I take outside this bracketed term, it will be x cube into this e raised to minus x, e raised to minus x, into, if I multiply by this e raised to minus x inside, this e raised to minus x, e raised to plus x, e raised to 0, and it will be 1 minus this e raised to minus x and raised to this minus 1. But we know this series as 1 minus x raised to minus 1 is equal to 1 plus x square plus x cube and so on. So using this, we can write this as x cube into e raised to minus x into bracket this 1 plus e raised to minus x plus e raised to minus 2x plus e raised to minus 3x, and we can write this as e raised to minus 4x and all these terms. So if I use this expansion here, or if I here, or if further I can solve this as this x cube, if I multiply by this e raised to minus 1 inside, then I will get here it as 1 sorry, if I multiply here, I will get this as e raised to minus x plus e raised to minus 2x plus e raised to minus 3x and so on. So if I use this expansion in this equation, so that I will get this as total energy density as E is equal to this 8 pi k raised to 4 t raised to 4 divided by this h cube c cube into integration 0 to infinity this as x cube e raised to x cube into bracket, we get this as e raised to minus x plus e raised to minus 2x plus e raised to minus 3x and so on, and the integration with respect to dx. But there is one standard integration that it can be used to solve this integration as integration from 0 to infinity x cube e raised to minus ax dx is equal to this 6 divided by a raised to 4. So we can apply this standard integration for each of the term, so that here using this standard formula, we'll get the E is equal to this 8 pi k raised to 4 t raised to 4 divided by this h cube c cube into, I can write this as into, I will write this as first, if I solve this x cube e raised to minus x dx, I will get this as 6 divided by 1 raised to 4. Plus, if I solve this x cube e raised to minus 2x dx, I will get this as 6 divided by 2 raised to 4. If I solve x cube e raised to minus 3x, I will get 6 divided by 3 raised to 4 and so on. I will get higher order terms. So I can take 6 as common, and so that I will get E is equal to 8 pi k raised to 4 t raised to 4 divided by this h cube c cube into 6 into bracket 1 upon 1 raised to 4 plus 1 upon 2 raised to 4 plus 1 upon 3 raised to 4 and so on. So this is nothing but a standard series, and we know that the value of that standard series is, if I write this as 8 pi k raised to 4 t raised to 4 divided by this h cube c cube into this 6, that value is pi raised to 4 divided by 90. So that is the standard value of this series. So if I put all these here, so I will get this equation as 8 divided by 15 into pi raised to this as 5 pi raised to just this pi raised to 5, change the color, pi raised to 5 into this k raised to 4 into this t raised to 4 divided by this h cube and c cube. So if you look at this term, 8 by 15 pi raised to 5 k raised to 4 divided by h cube c cube, this term is a constant term, and we can call that term as constant term, and I will write this term as E is equal to this. Suppose I will write A into this t raised to 4, where that constant A is equal to 8 divided by 15 into this pi raised to 5 k raised to 4 divided by this h cube c cube. So this constant is called as total density radiation constant. It is called as total density radiation constant. It is called as total density radiation constant. So that is how we have calculated the total energy density at that particular temperature. However, Stefan's fourth power law is defined as it is the amount of energy radiated per unit time per unit area. So if you try to calculate, or if you consider that, suppose there is this is a black body, and suppose there is a small aperture here, so that the radiation is coming out per unit area per unit time, and that energy radiated is given as, suppose that energy radiated is, suppose E dash, it is energy radiated per unit time per unit area. It is given by the equation 1 by 4 into this C into this E. So actually this is the expression for the energy density. We will take here directly. So the energy radiated per unit time per unit area is given by this quantity. So after using the value E, actually we will get the Stefan's fourth power law. So if you use this as E dash is equal to 1 by 4 into the C, and value of E is 8 divided by this 15 pi raised to 5 k raised to 4 divided by this h cube c cube into this t raised to 4. So if you solve this further, you will get this quantity as, this is nothing but 2 by 15, this you will get cancelled here, into this pi raised to 5 k raised to 4 divided by this h cube into this c square. So into this t raised to 4. So if you look at this term, this is again a constant, and it is called as the Stefan's constant. It is called as the Stefan's constant, and it is denoted by sigma. So Stefan's constant sigma is equal to, this is nothing but 12. Just let me. So this is nothing but 12. 2 divided by 15 into this pi raised to 5 k raised to 4 divided by this h cube into c square. So this is the Stefan's constant, and the value of Stefan's constant is given as, it is 5.67 into 10 raised to minus 7 watt per meter square into k raised to minus 4. This is the unit. So again, if you write this equation as and finally you will get this as E dash is equal to sigma into this T raised to 4. So this is the statement of the Stefan's 4th power law, which states that the energy, or which proves that the energy radiated per unit time per unit area is directly proportional to the 4th power of the absolute temperature. So in this way, we can obtain a Stefan's 4th power law from Planck's radiation law. So hope you might have enjoyed this lecture. If you like this lecture, don't forget to like and share my this video, and subscribe my YouTube channel so that I will prepare more and more lectures for you. Thank you for watching this lecture.